Hi everyone, welcome back to Geeks for Geeks practice. So in case if you have not registered for this Microsoft in 29 days self-paced course, which has a lot of benefits, so you can find the course link in the description of this video. And after you register for this particular course, then when you click on the start button, so what will happen? You'll get access to all the days that we have done up till now. And in these days, let's say if I consider day 14, if I open this day, so you will get what? You will get the recording of each day, the two videos that we do, the two problems that we do, recorded video editorials of those, and the 5 problems. That is 2 problems that we solve in the batch. Apart from this, 3 problems for homework. And you will not only get this much benefit, you will also get the access to the leaderboard and the discuss section. So you can discuss your doubts with the peers. Apart from this, you'll also get the access to the leaderboard where you can see your progress amongst other people. Now let us discuss this problem, largest binary search tree. So what we have to do here is, we'll be given a binary tree and we have to find the size of the largest binary search tree in this particular given tree. So here the size means the number of nodes in a particular tree. So let us first of all discuss what is a binary tree and what is a binary search tree. So if I talk about a binary tree, so a binary tree is nothing but a tree in which every node has at most 2 children. Okay, that is the case for binary tree. But what is a binary search tree? So in a binary search tree, what happens? Like in a binary search tree, if I talk about a binary search tree, so the root value, okay, if suppose there is a root value, so the root value is greater than the left child, and the root value is greater, is greater than the left child, and the root value is lesser than the right child. Okay, and this is true for all the nodes. Let's suppose that if I expand this particular tree here and make it like this. So if I make it like this, so this is a binary search tree. Why? Because you can observe that 5 is greater than 3, 1 and 2. So 5 is greater than all the values in the left subtree. Okay, and 5 is lesser than all the values in the right subtree. So that is why this is a binary search tree. Suppose in place of this 5, if I had placed a 4 here, so this would no longer be a binary search tree because there is a value existing like 4, which is lesser than the this root. Okay, so there is a value existing in the right subtree which is lesser than it. Okay, that is the case. So how can we check? So what you can try to do is, like, if you have to check that whether at a particular node, starting from a particular node, let's say you root the subtree here and you check that, okay, whether this subtree like is having, like, I should have made this as 4, sorry, then it would have been the subtree. This is a subtree. This particular tree is now a subtree. Okay, so the case that I took earlier, I did not see that I had made 2 here. So what will happen in this case, because for 3 also the right side should be greater and the left should be smaller. So for this case, what we can observe is that if we have to check, so we can start from here. If we start from here, then we can check it. But like if I have to check for, like if I start from here, so for this node I have to iterate through whole of the tree. For one node I have to iterate whole of the tree, that is order of n time, and check. So if there are n nodes, right, if I'll check for each and every node whether it is a BST or not, so that will take order of n square time, and that is very, very costly. So can we do something better than this? Yes, we can do something better than this. So what can we do instead? Instead of doing this, what we can do here is, we can simply say that we will try and find the values in the left subtree and the right subtree. So we will check what? If we want to check that whether 5 is a valid BST or not. So there are 3 conditions. The first condition is that the left child should itself be a subtree. So is 3 a subtree? Yes. So it will return a true, that okay, it is a subtree. Like it is a BST at this subtree. Is 7 making a BST? Yes, 7 is also making a BST. So if my left and the right children are making a BST, now the condition depends on me. Okay, now the condition depends on this 5, whether it can be a BST or not. So what should I check? Should I check for 5 and 3? No. Like should I check the value of 5 and 3 and the 5 and 7? No, I should not check this, because suppose if 7 is a BST like this, still like is still in this particular position. Suppose 7 as a child is 1, so 7 is obviously a BST, but this will not make a BST, right? 5 will not be a BST any longer, because if the value is 1, so in the right subtree every value should be greater. Okay, so what we can like, should we check it again order of n time? No. What we can instead do is, instead we can check the, like if you want to check, so what we can check is, we can try and find the maximum value in the left subtree. Okay, and we can try to find the minimum value in the right subtree. Why? Because if the maximum value in the left subtree, okay, if the maximum value in the left subtree is lesser than the root data, okay, first of all, the left subtree should be a BST and the right subtree should be a BST. Then if the maximum value in the left subtree is lesser than the root value, so that means all the other values in the left subtree are also going to be lesser than the root value. Fine. So that means the BST condition is holding true for the left subtree. And in the right subtree, if the minimum value, right, if the minimum value in the right subtree, okay, is greater than the root data, so that means if the minimum value in the right subtree is greater, so minimum value is 6 greater than 5? Yes. So that means if the minimum value is greater than the root data, so all the other values lying inside the right subtree would also be greater. Okay, that is what would happen. So what can we do here? So in this case, we can observe that we will be able to check whether it is whether the tree is a BST or not. We will be able to check these things, right? If we are asked to. But here we are asked to get the size as well. So for getting the size, what we'll have is, every node will return to its parent. Like, we will do a post-order traversal for this. And why we'll do a post-order traversal? Because we can observe, right? Something is returned from the left subtree, something is returned from the right subtree, and then the processing is done for the root. So that's nothing but left, root, and right, which is a post-order traversal that we are trying to do. So what will happen is, every node in this particular tree will return what? Will return a data packet, and the data packet will look something like this. It will have a count, that is the number of nodes in that particular subtree. It will have a boolean variable, that is BST. It will tell that whether rooted at that particular node, whether it is a subtree or not. Okay. Apart from this, it will store the minimum value in its subtree and the maximum value as well in its subtree. Okay, because I'll be using it. If it is the left subtree, then I'll check for the maximum value in it. If it is the right subtree, so I'll check the minimum value. Okay, that is what we will try to do. Now, if we are trying to do this, so how can we do it optimally? So what we will do is, suppose we call for the one, that is the leaf node. We call for its left and right. Okay, so what should its left and right return? So basically it should return 0 as the count, because the size is actually 0. It should return a true, because it should return a true, and this should also return a true, so that I can check for the other values, right? Okay, then because null is always you can say BST kind of thing. Okay, then what we'll do is, if we want to return the minimum value, so we'll return the minimum value as less as possible. So we'll return the minimum value as negative infinity, and we'll return the positive value as positive infinity. Okay, then for the same case, for this, we'll return 0, we'll return true, we'll return negative infinity, and we'll return positive infinity. Then when we come to this one, so its left child is returning a true, and the right child is returning a true. Okay, so that means its left and right is indicating that they are BSTs, although their size is 0, so maximum is still 0, right? Then what will happen? I am doing what? I am checking. So I'll check that 1. So for 1, what is the maximum value, minimum value, like what is the maximum value, right? What is the maximum value in the left subtree? So if I want to check the maximum value in the left subtree, so instead of doing this, what I should do is, if I want to check with the maximum value, so the maximum value should always be as minimum as possible, right? So if I'm checking for the maximum value, so maximum value should be actually int min, right? Because the maximum value should always be lesser, because for this leaf node, it should always be true, because leaf node will always be a BST. So I'll pass the maximum value as negative infinity instead of positive infinity, and I'll pass the minimum value as infinity. Why? Because if I am talking about the minimum value, so if the minimum value in my right subtree should always be greater than me. So if I'm at the leaf node, so the minimum value is what? Minimum value is nothing but positive infinity, a very high value. So the minimum value will always be greater. So that means it will abide by the condition of BST. Then the size of this BST, this will return what? The size will be 0 plus the left subtree size plus the right subtree size plus 1, that is nothing but 1. Okay, then I'll say that it will be true, it will return true, and the minimum will get updated to 1 and the maximum will get updated to 1 as well, because the minimum is here 1 and the maximum is 1 here. Okay, so my maximum size gets updated to 1 here. Okay, that is what happens here. Now what will happen if I talk about this particular value 6? So 6 will be a BST as well, as we can observe it is a leaf. So it will return what? It will return 6. The size would be 6, like the size would be 1 actually for this case, and it will return a true to its parent, and the minimum value will be 6 and the maximum value will be 6, that will be returned. And 9 will return what? 9 will return the size as 9. Then it will return a true as well. Okay, because it is a BST actually. And then what will happen here is, will also return 9 and 9, because the minimum and the maximum values are 9. Okay, then we check for, let's say we check, like 4 will also return what? 4 will return the size as 1, it will return true, and the minimum value for 4 will be 4, and the maximum value at the subtree 4 will be also be 4. Okay, then when I come to this 3, so is the left child for 3, is the left child returning a true? Yes. Is the right child returning a true? Yes. So 1 is returning a true, 4 is returning a true. In that case, what I'll check is, I'll check whether 3 is greater than the maximum value on the left subtree. Yes, 3 is greater than 1, which is the maximum value on the left subtree, so that means it would be true. And then if I check further, so if I check for the right, so is 3 greater than the minimum value in the right side? Yes. 3 is greater than is 3 lesser than 4? Yes, 3 is lesser than the minimum value in the right subtree. Okay, so in that case, what I will say is, I'll say that, okay, my count would be 3. Okay, my count would become 3 because 1 from the left, one size coming from the left, one size coming from the right, plus the root. So that means the size would be 3. Okay, then what will happen? This will return a true. Okay, 2 its parent, this will return a true, 3 will return a true. And then what is the minimum value that I've seen up till now? 4. In this subtree 3, I've seen the minimum value is 3, like minimum value is 1 and the maximum value is 4. Okay, that is what will be returned. And then from this subtree as well, so maximum gets updated to 3, maximum size is 3. Similarly, 7 is also a BST because 7 is greater than the maximum value in the left subtree, that is 6. So 7 is greater than 6 and 7 is lesser than 9. So that 7 is lesser than the minimum value in the right subtree. So that's why what 7 will return is, 7 will return 3. It will be turning true here, and then it will return what? The minimum value is 9 and the maximum value is maximum value is, minimum value is 6 and maximum is 9. Then what happens for 5? I'll check whether the left subtree is returning a true. Yes, so that means 3 is a, for 5 its left subtree is a BST, right subtree is also a BST, so it can have a chance to be a BST. So I'll check, is 5 greater than the maximum value in the left subtree? Yes, 5 is greater than the maximum value in the left subtree, so 5 is greater than 4. Okay, so that means the left condition is validated. Okay, now I need to check for the right. So is 5 lesser than the minimum, is 5 lesser than the minimum value in the right subtree? Yes, 5 is lesser than the minimum value in the right subtree is 6. So 5 is lesser than it. So that means 5 will be lesser than all the other values as well. So that means the by search condition is true. And what I will say is that the count now changes to what? 3 from the left subtree, 3 from the right subtree. So 3 plus 3 is 6 plus 1 7. I'll return a true. And then the minimum value will be 1 and the maximum value will be 9. Okay. So now I'll update my maximum with the count. So since the count is now 7 and this returns a true. Okay. Since this is a BST, so that's why I'll check the count. So count is 7, which is greater than 3. So I'll update my maximum to 7. That is how I'm doing it. And for doing this operation, we are applying the post order traversal and it is taking order of n time. We are using data packets which are containing the count or the number of nodes in the subtree and telling us true or false whether the root, whether the subtree at the given root, at the particular root is a BST or not, storing the minimum value in that subtree and the maximum value in that subtree. Okay, that is what we are trying to do. Let us try and check out the code as well. So what we'll do is we'll make this data packet. I've named it as pair. You can name it anything. First of all, you can store the count. You'll store the BS, like whether it is BST or not, you'll store the maximum value, you'll store the minimum value as well. Then what will happen, we'll have a maximum, right? In the main function, we'll have maximum declared as 0. Then what we'll do is we'll call for this recursive function by passing the root. So we'll call this is BST function by passing the root, which will be doing the post order traversal. So we'll make a pair. Okay, first of all, we'll make a pair. And suppose if the root is null, okay, so in that case, we'll pass p is equal to 0 because the size would be 0 of that subtree. It will return a true, and we'll pass the minimum value as maximum because if we want to check for the if we are at the reef node and we want to check the minimum value in the right subtree, so the minimum value in the right subtree should be greater. So that means I'm passing int maximum so that the leaf node becomes a BST for the leaf node. If the roots left and the right is null, so it should validate. Then the maximum value I'm passing it is int minimum because if I'm checking for the maximum value in the left subtree for the leaf node, so it should be maximum value in the leaf maximum value in the left subtree should be lesser than the root data. Then I'm returning this, and then I'm calling the post order traversal. So basically what I'm doing is first of all calling for the left child, calling for the right child, and this returns me the data packets. Okay, so I'll update my minimum and the maximum with this root data as well. I'll update the minimum and the maximum for the current root. Okay, then what I'll check is I'll check that is the left subtree true. Okay, is the left subtree making a BST and is the right subtree is making a BST? If it is so, then I'll check that is the maximum value in the left subtree, if the maximum value in the left subtree is lesser than the root data and the minimum value in the right subtree is greater than the root data, so that means it will be a BST, and I'll mark the BST as true for this particular node, otherwise I'll mark the BST as false. So what we'll do is we'll update the count of the number of nodes in this particular BST after this. And what we'll do here is we will say that if the particular node is a BST, right? If the tree rooted at this particular node is a BST, then we will say what? We'll update our maximum as mx is equal to nothing but maximum of mx comma count, the number of nodes for this particular subtree. And then we'll simply return the p. So this is how we are doing it in order of n time. So for doing this, it takes order of n time, and the recursive stack space, the space complexity will be order of height of the tree. So in case if you understood this explanation, make sure to hit the like button. Thank you. In this video, we will discuss the problem boundary traversal of a binary tree. So the problem says that we'll be given a binary tree and we have to find its boundary traversal. So the traversal should be in this order. So suppose a binary tree has been given to us. So first of all, we'll put all the left boundaries in the answer. Then we'll put all the leaf nodes. And after that, we'll put all the right boundary nodes in the reverse order. Let us check the sample example for better understanding. So suppose if we have been given the example like this, okay? Suppose this is the example that has been given. The example is 1, then 2, then 3, then we have been given 4, then 5, then 6, then 7 here, and with 5 we have connected 8 and we have also connected 9, okay? So if this example has been given, so first of all, what will be the boundary traversal? So first of all, this node will be there, okay? Then this node, okay? So I'll highlight it how we are doing. This node, then this node will be the boundary, like this will be the leaf node, then this node, okay, because we have only just this node as the left node, then this node, okay, then this node 6, that is another leaf node, then this node 7, okay, then after that this node 3, that is the right boundary, okay. That is how we will be traversing it. So first, like what we will do here is, like basically suppose that instead of this we had another example. Suppose the example was 1, 2, 3, 4, 5, 6 and 7, okay. If this was the example that was given to us, so in this particular example, if we will try and observe, so what happens here? In this example, we will see that first of all we'll have this node, okay, then this node, then all the leaf nodes, and after that we'll consider the right node in the reverse order. So basically all the right nodes, all the right boundary nodes that we see, they will be considered in the reverse order, okay. That is what the problem is saying. So how can we do it? So for doing this type of a problem, what we will first of all do is, like if the root is null, okay, so like we will try to build the answers one by one. So suppose that if the root node is null, then what we will do? So if there will be some edge cases, suppose if the root node is null, in that case we'll simply return the empty answer, because there is simply return the empty vector, because there will be no node, okay. Otherwise, what if there is just one node present? So if there is just one node present, okay, so if the root right, okay, if the root's left child is equal to null, okay, and the root's right child is also equal to null, right, in this case what we will do is we'll simply return what? We'll simply return the root data in form of a vector, because there is just one node. Otherwise we will traverse, okay, otherwise we will do what? Otherwise we will declare a vector answer, and then we will try to do three types of traversals, right? Basically we'll do three functions. We'll write three recursive functions that will help us to get the nodes. So first function we'll write for getting the left side node. This is the root node, so we'll directly insert this in our answer. Then we'll get the leaf node. So this is a leaf node, okay, so this 2 will be a leaf node. This is the root node actually, right? This is the basic root, this is the left boundary. Then we'll consider all the leaf nodes. So 4, 8, 9, 6 and 7 are the leaf nodes, correct, because they do not have any child. And then, so if we want to consider this, then this, then this, then this, then this, so basically we can do an in-order traversal. That is, first of all we'll consider left, root and right, and we will keep on inserting the root data one by one, okay. That is what we can do here. Now if we observe for this part, so we will consider the right views as well, okay. So how do we do this? So for doing this, what we will do is, first of all we'll get a function for finding the left, okay. So how do we find it? So suppose instead of this case, if we were given something like this, suppose instead of this tree we were given something like this. Suppose if this thing was given to us, like let's say values, let's say 7 was given here, then another value, let's say 5 was given. So in my left view, what will be the nodes that would be included? 2 would be included, 4 and 7 would be included, okay. So what I will do is I'll write a function left like left boundary, okay. I'll write a function, let's say left nodes, and in that I'll pass the left node of the root, okay, initially. So I'll pass 2. So what I will do here is, I will say that for this particular node, I know that I'll be inserting it, right? So currently in my answer, I have only inserted the node 1, that is the very starting node. After this, what I need to do is, I need to insert, like, does this node have a left child? Yes, it does have. So first of all, I'll insert this 2, and then I'll move to its left child, because it does have a left child. Okay, so I'll move to this node. Then does it have a left child? No. So if it does not have a left child, so no problem. Does it have a right child? Yes. So first of all, I'll insert this 4 in my answer, and then I'll move to the right child. Why I've moved to the right child? Because this right child now is also considered in the left view. Okay, that is why. So if the left child is existing, so basically that will be my left, that will come in my left boundary. Otherwise, if the for the current node, if the right boundary is existing, so that means I'll move to it. Okay, so for this 7, I will simply say that, okay, let's store this. Then I'll move to the left child. So the moment I move to 5, so is 5 actually a leaf node? No. Well, like, is 5 actually a boundary, left boundary node? No, it is actually a leaf node. So I'll not be saving it here, because it does not have a left, like 5 does not have a left node, like 5 left is null, 5's right is null. So in that case, I'll not be storing 5 here. Okay, that is what I would do here. Now this is how I'll write the left node function. So what I would do is, first of all, I'll insert in my answer, I'll simply insert the root data first of all. Okay, and after inserting the root data, what I would do is, I would simply call a function that will be recursive. So that will be called for the left node. So I'll name it as left node. That will help me to store all the left nodes. So I'll call from where? I'll call from the roots left. Okay, from the initial root that has been given to its left, I'll call, and I'll try to update my answers. So what I'll write there? So I'll write void leaf nodes. Okay, and here what we would write is, we would write node star root comma vector int ampersand answer. So suppose, like, what happens when will I return from this call? If my root is equal to null. Okay, if my root is actually null, if I've reached a root that is null, so I can simply say that I can return from this particular recursive call. Okay, how? So let us say that if the tree was something like this, if I had 1, then I had, let's say, 3, let's say I had 5 here, 7 here, something like this. So if this is null, right, directly, so I'll return from it. So these are the cases when I'll return. If the left child, like if the root is, if I've called for this function and the it is not existing, so I'll simply return null from it. Okay, like basically I'll simply return from this particular recursive call. I don't even need to return anything. Okay, then what I'll do is, I'll check that if for the current root, does its left root exist? Yes. So that means it is not a leaf node. Okay, if its left child is not equal to null, okay, if the left child of the current root that I am at, if it's not equal to null, so that means the current root is not a leaf node, so it's a left boundary node. So I will say what? I'll say that, okay, let us insert this particular node in my answer. So I'll insert the root data in my answer, and I'll say that, okay, if its left child is existing, so let's move to the left child. So I'll say that sorry, I've written the boundary. So left, I should write this function as left node. Okay, so I'll write this as left node. Then I'll go to the left child. Okay, and I'll pass the answer. Okay, so that it gets updated. Now else if suppose that the roots right is not equal to null. Okay, in that case, what would I do? If the root nights is not equal to null, so I'll simply push back what? I'll simply push back the root data, because that will be what? That will be a boundary, left boundary node. And then what I'll do is, I'll call for the left nodes function, and I'll call for the right child now, because right child is existing actually. So I'll call for the right child and the answer. Okay, that is what I would do in this function. After this function has been done, so I need to store what? I need to do the leaf. I need to do the traversals for the leaf in the given tree that I have. I need to also do the traversals for the leaf nodes. So how would I do the traversals for the leaf node? So what I would do here is, I would simply start from the, like, I'll write a function leaf. Okay, recursive function, and I'll traverse all the leaf nodes. Whichever leaf nodes I get, I'll store them. So I come here. So does this node is a leaf node? No, because its left child and right child both are existing, so it's not a leaf node. Then what I will do is, I'll do the Inorder Traversal, because I want to store them in this fashion, in the normal fashion that I have. So let's get the tree back that was originally given to us. So if it is 8 and this is 9, suppose. Okay, so what I would do is, I would come to this 2. When I come to this 2, so is it a leaf node? No. So I go to the left child. So when I go to the left child, so it is 4. So it is a leaf node actually, it does not have any children. So actually in the answer, first of all, 1 was stored, 2 is also stored because 2 was a leaf node, like 2 was a left node. Okay, then there is no other left boundary. Then 4 is a leaf node, so I'll store 4. After this, like what will happen, like let me write the answer like this. So the answer had initially 1, that was the root node. It has this is the root node, this is the leaf left boundary node. Then I'll insert 4 as well. Then I come back to this, and then what I do is I move to the right child as well. So when I move to this node, so is it a leaf node? No. So I move to its left child. So is 8 a leaf node? Yes, because it does not have left and right children. So that's why I'll insert 8. Then what I'll do is I'll come back from here, and I will when I come back after the Inorder Traversal, so I'll call for the right child of the root. Okay, when I call for the right, so what happens for the when I call for the right? When I call for the right, so this I call for this 9. When I call for its left is null, its right is also null. So that means I'll store this particular thing. So I'll store 9. Similarly, I'll store 6 and 7 as well using this Inorder Traversal. Okay. So what I will write here is I'll write a leaf function, and in this what I'll pass is I'll pass the root and I'll pass the answer so that it gets updated. So what we will do here is we will have the void function here, like leaf function, because I'll now be storing the leaves. And what I would do is I would pass node star root. Okay, and along with this what I would pass is I would pass vector int answer. Okay, that is what I would do. And what we will do is if the root is equal to null, okay, then we can simply say that we will simply return from the recursive call. Otherwise, what are the circumstances that we'll store? So I will check for few conditions, right? First of all, what I will do is I'll call this leaf function, because this is an Inorder Traversal that I'm doing. So I'll call this leaf function first of all for the roots left. So first of all, I'll call for its left, and it will update all the leaf nodes in the left subtree. Then what will happen? I will check that is the current root that I'm at. If the current root that I'm at, if its left is equal to null, okay, if the current root that I'm at, if it is left is null and its right child is also null, okay, if the left and the right both are null, so this indicates what? This indicates that the current root that I'm at, it is a leaf node. So I'll store it in my answer. So I'll simply say that answer dot push back the root data. Then what I would do is I'll call the leaf. Okay, I'll pass the root and I'll pass its right. Okay, and I'll pass answer. So this is the Inorder Traversal that I'm doing. First of all, I'm calling for the left subtree, storing all the leaves in the left subtree, all the leaf nodes in the left subtree in my answer. Then I'm checking that if the current root is actually a leaf node, so that means its left and right child are not existing. So I'll store it in the answer, and then I'm calling for the right subtree for storing all the leaf nodes in the right subtree. Okay, that is what I'm trying to do. So that is what we have done. Now we need to do the right nodes as well. Okay, we need to store the right nodes in the reverse order. So what we'll do is we'll pass the roots right. Okay, and we'll pass what? We'll pass the answer here. And what we would like after this part is done, so we can simply return the answer that we have calculated. So what we will be doing here is we will simply say that we will write a void right nodes function. Okay, and I'll pass what? I'll pass the root node and we'll pass the vector int answer here. So you have to understand what we can do here. So if I talk about this particular function, so what we will be doing in this function is, if suppose that the root is equal to null, okay, suppose that the root was null, so in that case we will say that okay, we'll simply return. Otherwise, think of the circumstances. So what we will do here is, like, we have to, if we were at the left, so then we were going to the left child, but now suppose we start from here. So when I am at this node 3, so is it a leaf node? Actually no, it's not a leaf node. Okay, so if it is not a leaf node, so then what will I do? If it is not a leaf node, I will simply say that we will insert it, like, does it right exist? Yes, because I will be always concerned about the right children. Okay, I'll always be concerned about the right children if they are existing, because right boundary will consist of the right nodes. So if I am concerned about the right children, so current node left right node is existing. So first of all, I'll check for the right. Is it actually existing? Yes, it is existing. So if it exists, so I'll move to it. Okay, then I'll check, is the right child existing? No, it's not existing. Suppose in this case, if the left child was existing and it was something like, let's say 10. Okay, if this was existing, so I'll move to the left child actually. Okay, then I will check for its right child is existing. No, its left child is existing. No, then I come back, right? Then the recursive call comes back. When I come back, then I'll store 10. Okay, then I go back. When I go back, then I'll store 7. When I go back, then I'll store 3, because I have to store these values in reverse order. I have to store the right boundaries in reverse order. Okay, that is what we have to do. So similar concept as we did in the left part, but just a bit of change. So if the if the roots right, because I'm concerned about the right boundaries. So if the roots right is not equal to null, so that means that the current root is actually not a leaf node and it's a right boundary node. So I'll do what? I'll first of all say that we will not store it, right? We will not store it while we are backtracking, right? While we are moving back, then we'll store, because we want to do what? We want to store these nodes in reverse order. So I'll say that we'll call the function right nodes, okay, and we will pass what? We'll call for the right child and we'll pass the answer so that it gets updated. Okay, after I come back to this particular recursive call, after I have stored, let's say when I called for 3, like let's say when I called for 7, right? When I called for 7, so 7 answer gets updated to 10. Okay, because it's the like when I come back here, right, 10 is not having any so like 10 is a leaf node actually, right? So since it is a leaf node, so nothing will happen. Then when I come back, right, when I come back, so 10 is actually not stored for me because 10 is a leaf node. Okay, so what will happen here after this? Like after 10 was stored, so I have this value 6, like I have this value 7. So this 7 is a right node. Okay, so I'll store it. Then when I go back from this recursive call, then I'll store 3, because I want to store what? I want to store the right nodes in reverse, like right boundary nodes in the reverse order. So that's why while I'm coming back to the function, then I'll update my answer to the current root data. Okay, that is what we will do. And otherwise, as we mentioned, like else if suppose that the roots left boundary is not equal to null, so in that case what we will do is we'll say that right nodes will pass the function right nodes will pass the roots left child. Okay, we'll go to the left child, we'll update our answer. Then when we come back, so then what we'll do is we'll push back the root data. Okay, that is what we'll do it. So this is how we are saving our right boundaries, and then we'll simply return the answer. Let us try and compile this code as well. Okay, we are getting a compilation error. It says that push back in the line number 109. Let us now try and compile it to see if there is any other error. Okay, one more error is there in the line number 157. Okay, so the error is what? The error is, it says that left node was not declared. Okay, did I not declare it properly? Let me check. Left nodes. Okay, so the function name is actually left nodes and not left node. So let's see if it works. It works on the samples. Let us try and summarize this code as well. So you can see that our solution was able to pass all the test cases. And talking about the time complexity of this code, so since we are moving to each and every node exactly once, so the time complexity will be order of n, and the space complexity will be nothing but the recursive stack space, that is order of height of the tree. Thank you.